for direction like north, south, east, west, I just put west, north, east, south. What difference does it make? It's just a name. It doesn't really have any meaning to it. You know, we attach a meaning to it in a relative way, but that's all. And the same thing with a clock. You know, instead of 12, 3, 6, 9, you know, you could have 6, 9, 3, 12. It doesn't matter. It's just a concept, and it doesn't really exist. So, you know, getting back to this, times of latitude and longitude, time, and then lines of latitude, longitude, they don't really, they're a concept, they're abstract. They don't really exist. Okay, so if we know they don't exist, then what happens? Well, because of this, right, as concepts, neither time nor lines of latitude and longitude exist. Because of this, neither Minkowski flat space-time nor Einstein curved space-time exist, right? So this is sort of where all this, you know, my rambling on here, but this is basically where it all focuses down to, is this, right? Because they're abstract time and lines of longitude, but I'm going to eject time. We're going to eject lines of latitude. I want to focus on time, right? Because of this, time, it's an abstract concept that doesn't exist, right? Because of this, neither Minkowski flat space or flat space time. Let me start over. Because of this, neither Minkowski flat space-time nor Einstein curved space-time exist. Right? They don't exist. In fact, it was Minkowski that first came up with this idea of putting time, embedding time into the three spatial coordinates, right? So that was with flat time. Einstein did it with what? Curved space-time, right? That's what he's doing, embedding it. And then I'm saying, well, but neither one of them exist. Neither Minkowski space-time, flat, or Einstein's space-time, curved, exist, right? So why is this? And the answer is a three-dimensional space can't have embedded or be infused with a concept that doesn't exist. So if you're trying to take something like time that doesn't exist, it's completely abstract, and you're trying to embed it in a three-dimensional space, you know, whether it's flat like Minkowski's or whether it's curved like Einstein, it's not going to happen. It doesn't exist. I mean, you can have the three-dimensional, you know, the three axes, right, for a three-dimensional space, but there's no way to put time in there. It doesn't exist. How are you going to make it exist? Even in space, the axes for the three-dimensional space or three space, you know, it's there. Whatever, it might be something in there. It might be a vacuum. It's there. Whatever. Time isn't. You can't stick it, or embed it, or infuse it into a three-dimensional space model because it doesn't exist. And that's what we talked about other page. Right? Newton knew of this, right? Newton knew as far as gravity goes and time and all, he knew this. He didn't see time as being infused within space. He saw it differently. And like I said, Minkowski was the first to sort of mention it, and Einstein picked up on it, but it has no meaning in reality, right? Like the general theory basically has no meaning in reality. It's an interesting theory, that's about it. So Newton knew of this about time, and he kept it, time is totally independent of space, right? Time is totally independent of space because it's a relative term, but in reality it doesn't exist, right? So time is totally independent of space. You know, so here's another question that I was, you know, when I was going back and looking or studying space-time, especially the general theory, it's like, well, how do you get time in there? How is it, how exactly do you bend time? It's like, how does that work? And basically I've come to the idea that it doesn't work. It's an interesting idea, but it has no basis in reality because you can't fuse it into a three-dimensional space model because time doesn't exist. It doesn't work. I mean, it's a nice model, interesting, doesn't work in reality. If you're looking for reality, that isn't it. The general theory, the special theory, they're not it. So, right, how Newton knew this, right? Time is totally independent, totally independent of space. You can't put them, you can't fuse them into each other because it won't work. And time, you can't bend time. There's no way to bend time. Even in the space-time, you can't bend time. Einstein's idea about bending or curving or warping space-time, yeah, there's nothing there. It's an interesting point, maybe theoretically, but that's it. So, I just wrote just a couple of things that I wanted to touch on. One was time travel, right? So a lot of people are thinking about going forward into the future, or going back in time. Time doesn't exist, so I have no idea how that's even possible. I have no idea how you could even do that. Time travel, not really. But I did make up this small little diagram here. And if we have Earth over here, and we have the Sun over there, and let's say they're 1 light year apart, the closest you could come is saying, well, as I travel, if I go from Earth, if you're on Earth, then you'll see the light from the star as it leaves the star 1 year later, right? So you're seeing the star how it looked a year ago. As you move towards the star itself, then you'll see closer to the actual time it leaves the star to the Earth. So in that sense, you'd sort of be more current with it, at the time. And going backwards the opposite way, as you remove yourself from the star, right, and you go back towards the Earth, then you're going to go back into what the star looked like a year ago, which is sort of back in time. That's about the closest I can get to coming up with some kind of time travel. I don't see how it's possible, really, but future generations will pick up on that. The other thing about time is, if you're going to try and infuse time into three-dimensional space, then it's not just like going between 2 points. That's interesting. It means up here you have to infuse every point in space with a time component, its own individual time component for a whole universe. Not just a little area, but you have to have a time component for the whole universe. And then how does that move? Or how does that change, right? I don't see any way you can do it now. That's a rather daunting task. But that's what it is, right? That when they're talking, well, especially with the general theory, they're talking about infusing or embedding or injecting time directly into the three-dimensional model. Time is the fourth, but you have to have time every point in space. I mean, even if you're looking at this living room, you'd have to have a time component for every point in space, not just here to there, right? So that's not going to be possible. Yeah, so you have to put a time component, and that's what it means, and you can't do that, so that's why it fails. Bonus. This is just something else. Time dilation, the special theory of relativity, not possible, right? If you don't have time, and time isn't real, then you can't dilate time, or expand it, or slow it, or anything else, right? You can't do that because it doesn't exist. I mean, you can draw an equation for that, right? We all have seen the equations, but it has nothing to do with reality. And that's what's going on with the special theory of relativity and the general theory of relativity. It has nothing to do with reality. Like I said, it's an interesting idea, but going forward it has to be dropped, both of them, because they have nothing to do with reality. So you can't have time dilation. Time doesn't exist, okay? And you can't bend time, like in the general theory, you know, either by itself or within space-time, and somehow you can't bend time. There's nothing to bend there, right? It's like bending loyalty. How do you bend loyalty? I have no idea. So, yeah, so you can't slow or expand time because time doesn't exist, okay? So that was kind of my point, that the time is up for space-time. So if you look at Minkowski space-time, or you look at Einstein space-time, you know, interesting, but have nothing to do with reality, right? Time is independent of space. It's not a part of space, it's independent. And people who speak of space, you know, being a fabric that's kind of moving out, whatever, no. It's not a fabric. It is not. It's what Newton thought it was and was, right? It's just sort of this emptiness with whatever else is in it. So, all right. Well, let me see what else. Oh, there's nothing. Well, you know, I do have one idea that in fact, one of the ending of one of my previous videos, and I talked about this, how these periodical science magazines, not journals so much, but periodical magazines, talk about Einstein, and it's sort of like, Einstein wins again, you know, Einstein tops them all. It's kind of like, they almost think of it as some kind of game, and I don't know where they get that from, but this is just sort of a little comment I made about it. Yeah, science periodicals take Mr. Einstein's achievements too far. I've mentioned this before at the end of some of my other videos. I give another example of this here. So this is recently published in the journal Astronomy and Astrophysics. I think this is pretty recently, like the 10th of June or so. An experiment was conducted on gravity using a system of 2 white dwarf stars and 1 pulsar. To me, the experiment did little more than demonstrate the obvious. Cosmological objects, whatever their mass, are equally susceptible to gravity, right? It's nothing more than that. The problem is what the science periodicals wrote afterwards that's misleading and problematic, right? So these aren't scientists per se, they're science writers.